Hello, everyone. Welcome to this afternoon's general session. We have 3 talks going on right now for the general track. I'm really looking forward to hosting this session. So before we get started, I just want to give you a couple of ground rules. One is, ground directions. One is if you want to ask questions, ask in the Q&A, or you can raise your hand and we will bring you up on stage at the end. There'll be about 5 minutes for questions at the very end of the session, and I'll try to make sure to call on them. If you see a question you like, make sure to upvote it so we can make sure that that question is asked. And yeah, welcome again to the general session. I'd like to introduce our speaker today. This is Gregory Carr, and take it away, Gregory.
Awesome, thanks for having me. So today I'm going to talk to you guys about fuzzy environments for the perturbation, evaluation, and application of uncertainty quantification for Monte Carlo arithmetic. Now that's a mouthful. So I'm going to start by breaking it down into a few simple pieces, and then we'll go from there. So first of all, I'm going to introduce the concept of numerical stability. By numerical stability, essentially I mean something that some of you may be familiar with as conditioning. It's basically the sensitivity to small changes that a system demonstrates. So if you have a system that's highly unstable, you'll have something maybe like this arch right here. And when you push the ball in a tiny bit, in small amount in one direction, it'll end up rolling off and you'll have a big change in your result. This is, again, considered unstable. Now, there's other systems where, like this upside down arch, when you push the ball a small amount in any direction, it'll ultimately come back to a very similar resting state. So there's eventually a small change. This is considered very stable. Now, different functions and operations and things we do to our data as we're analyzing it have different stabilities. And you can can evaluate the stability of some operations in a closed form solution. Again, this is like a condition number. But when you're doing things like nonlinear registrations and optimizations and applying different sets of components in a scientific pipeline, it's very difficult to get a sense ahead of time how stable or unstable the entire workflow will be. So uncertainty quantification is the process of introducing generally small perturbations to tools and then studying the impact that they have on these results. So the way we're going to kind of be hanging out for the next half hour is I'm basically going to start by giving some examples of numerical instability in a particular scientific field. In this case, I'm talking about neuroimaging. That's where I generally spend my time working. Again, I'll give a bit of introduction on what that field is as well. Then we're going to go into floating point arithmetic and talk about some of the issues that arise there. There's going to be a bit of an interactive portion, so get ready over the reaction buttons, and I'll try and put a poll too if I can figure out how to make all that work properly. Then I'm going to introduce something called Monte Carlo arithmetic and a set of libraries called fuzzy environments. And then we're going to demonstrate how this can be useful in a few different contexts and talk about how you guys can take it forward into your worlds as well. So I'm going to start with, again, introducing neuroimaging. So neuroimaging, basically brain imaging, you start with a picture of a brain, something kind of like this, although it's generally not quite so pink and pretty. And you can turn these into surfaces, into networks, or so much more. These essentially, this is the way neuroscience is typically performed in humans through things like, again, MRI, EEG, MEG, so on and so forth. But again, you take these pictures, then you do some analysis on it, and you do your best to estimate and understand the structure of the brain or function. Now, these analyses are pretty difficult. Not for the least part because generally there's no ground truth. It's not like we can only study cadavers or things like that. If we're trying to look at behavior in the wild and we're trying to look at brain activation, it's not like we can take somebody's brain out and look at what it was doing at that exact moment. So the best we have are proxy measures. And, involved in the processing, we have image alignments, both linear and nonlinear alignments. We have different types of denoising depending on the data you're collecting. We have segmentations, we have surface generations. You're sometimes modeling different types of phenomena, including like heart rate effects or breathing effects, or actual brain activity effects. Then there's also things like feature selection and embedding that end up going into the processing of this data before you do some downstream analysis. So there's lots of different complicated steps. And again, the reason why this is a nice exemplary domain of numerical uncertainty and uncertainty quantification is because most domains involve some amount of some of these things. You know, whether you're working even in speech processing or other type of image processing, some of these issues are likely to be familiar to you. So we're going to start talking about some examples of uncertainty or just error in neuroimaging. So is the flicker coming through properly? Hopefully. It looks like it is from my screen. So, okay, good. Thanks for the thumbs up. So what you can see here in this flickering are different segmentations of a brain. And the only difference between these two images that we're flickering between is whether or not the segmentations were generated on a system running CentOS 6 or one running CentOS 7. Now that's, you know, I can hear the questions already. Well, were they using the same tool? Well, were they on the same data? Well, were they on the same system? Yes to all of these. They were using the exact same configuration, exact same parameters, everything. The only difference was instead of using it inside of a Docker, I think it was Singularity actually, a Singularity container that was based on CentOS 6, it was one based on CentOS 7. Now, this is a bit worrisome, as you can imagine. Imagine if you care about analyzing the region of the brain right over here where I put this blue arrow. Well, you might be a bit discouraged because all of a sudden you have tons of variability just from changing your operating systems. So, okay, let's jot that down. So that's one of the possible sources of difference. Now, we can also see sources of error or change due to small amounts of noise. Now, this is potentially not very surprising. We add noise in, we get noise out. This is the small push experiment I mentioned before. But the degree to which that we can, you know, put a tiny push and see a big change can be pretty impactful. So in this case, what we did, or what a colleague of mine did, was took a single voxel. So again, a voxel is just a three-dimensional pixel. They took a single voxel in the middle of the brain. So basically right here where my cursor is here, in case anyone's lost, I'm just making it bigger. Right here, they took one voxel, perturbed it by 1%. In other words, if the voxel intensity was originally 100, they made it 101. Then they reran the same software for generating these brain surfaces from the MRI multiple times, and everything that is not green is change. So this is a bit concerning again, because what you can see is you see some portions of the surface, excuse me, that are heavily inflated, other portions that are quite deflated. Deflated is blue, red is inflated. And even some of the inflations are actually denoted in gray, where it's just too big and it would distort the color map to even look at. So this is, again, a bit concerning. Tiny amounts of noise are really causing pretty drastic, widespread changes, not just local changes, but widespread changes. Now, again, another thing that may be somewhat obvious is another thing that can lead to differences or the sensitivity to these types of errors, the sensitivity to these types of changes and noise, is really your algorithm selection. So one form of image processing in the MRI world is something called tensor reconstruction. You can get these MRI images that are called diffusion-weighted images. Basically, they show you what direction water is trying to flow in the brain. And when you reconstruct these, you can kind of reconstruct, or at least the idea is that you can kind of reconstruct the pathways by which brain signals travel. You can reconstruct white matter pathways. So there's different ways to conceptually reconstruct these tensors, all with the same general purpose. And depending, because these are generally closed form solutions, relatively simple models, you can compute their analytic stability or condition. Now, what you observe in the wild is pretty consistent with what you'd expect. As you have a high condition number, in other words, something that's very unstable, you tend to observe considerable amounts of variability. As you have a more stable algorithm, as you'd expect, you tend to have less variability in the wild. Now, again, this is basically saying you can solve the same problem multiple ways, and some will be pretty good, and some will be pretty sensitive to noise. And part of the problem with this is they won't even be consistently sensitive. So what you can see over this plot on the right is you may have a function that when you're looking at, say, this right side of the plot here, I guess that is all ranges of theta and phi is very low. When you have low phi in this case, the pipe or the tool, the algorithm is quite stable. However, once phi gets up near 90 degrees, it's a mess. And you have some places where it's incredibly unstable, other places way down here where it's a very stable tool, probably even more stable than the baseline, and so on. So really it becomes an incredibly messy space to characterize, especially analytically, if you don't know exactly where your data live. Now, more fundamental than all of these is simply that computers are imperfect. And so regardless of if you say my data isn't noisy, my algorithms are super stable, I've tested on all operating systems and I don't see these problems, whatever. If you simply are doing floating point arithmetic, for example, as you see here, 0.2 plus 0.1, you will have possible errors. And that's not to say everything will be wrong. That's not to say, you know, throw the baby out with the bathwater, reinvent the floating point format. That's not it at all. The point is simply that there is imprecision in the way we're handling floating point arithmetic. And that means that both that gives us room to have errors creep into our results, and that gives us a place where we can potentially perturb these errors and understand them a little bit better. I see that there's something in the chat, but I can't see it yet. Let me just go check. Computers are perfect. I mean, they are kind of perfect in some ways. Is the correct answer to a different question? I'm not sure if I understand, Tom, but ignore me if I'm don't need to pay attention. But anyways, so the reason why we see a situation like we did above is because of the floating point data standard. And again, I'm not saying there's a better data standard, because personally I don't really know of one that's better across the board. But floating point data or decimal data, actually more precisely real data, is stored on disk like this. You have 1 bit that's dedicated to the sign, you have 8 bits dedicated to the exponent, and you have 23 bits that's dedicated to the fraction, or it's called the mantissa. Now, based on the combination of basically binary ones and zeros in these different points, you construct your number. Now, when you remember the example I showed you before, if you have 0.1 or 0.2, which is just, you know, an integer multiple of 0.1, you have a repeating fraction in decimal. So what that ends up meaning is at some point when you get to the end of this bit space, you will have an inexact representation of that 0.1. So because the arithmetic itself and the data itself are finite, the computations, as I said, can end up being inexact. So we're going to have a pop quiz. I'm going to publish a little poll now. Again, let's see if I successfully do it. Do I want to show the poll on the stage? Not yet. So let's see. What I want you guys to do is to tell me which is the correct answer to this problem. We have 2000 plus negative 1998. Or if you could show my slides again, please. Thank you. Plus 1.33. Depending on the order of operations we do here, if we do our 2000 plus negative 1998, or if we do our negative 1998 plus 1.33, what would the correct answer be? And again, to excuse me, to break down the question a little more, let's just assume we're working in not just a perfect world, not in the space where we have infinite precision, we can represent all our data as precisely as we want. We're working in a floating point world, which means that we can only at any point keep around 4 digits of data. So what I'd like you guys to do is either, again, react or answer the poll as you wish, whatever's easier, with whatever you think the, oh, my slides still sharing? I can't see them at the moment. Where did they go? Present to audience. Oh, apparently turned off. Okay, sorry about that. Not sure what happened. Okay, got the slides back. Sure we are. Cool. Okay, so I see ta-das because people are happy about slides being back. A couple trophies, a couple laughters. Okay, so there seems to, oh, and a few sunglasses. All right, so what we're going to do is we're going to break down these two evaluations. Most people are excited with the 3.0. Okay, we're going to break down both of these and see how many digits of precision we actually have at the end of the day and what the right answer is. So in the first case, we start off with 2000, we subtract 1998, we end up with 2 point a bunch of zeros. But we don't really know what's beyond this point because we don't know what's beyond the decimal point in either of the original numbers. So we end up having digits that are imprecise. These are not known values, so we end up taking 4 bits of precision, or 4 digits in this case, and turning them into 1 digit of precision. This is called catastrophic cancellation. So we've lost a lot of information. Even when we add our 1.33 at the end, because we don't really know what those zeros are, we don't really know what those, if we can trust those 333s. So in this case, again, we end up with 1 digit. Now we'll look at the other. So in this case, we do our negative 1998 plus our 1.33 first. So in this case, we have to get rid of some digits. So first of all, we start with, in a much better situation, we start off with 7 digits of precision here because we have 4 from over here. And then we have these extra 3 that weren't captured in the 1998 value. Excuse me. So we start with 7. However, we're going to have to throw away some of our 3s. So now we're down to 4. So this is progress. But then again, we have this 2000 minus our 1997, which is more catastrophic cancellation, and we again end up with 1. So in both cases, the way these expressions were formulated, we went from a situation where we had at least 4 digits of precision in all of our input data, and our result only has a single digit of precision. Neither of these answers is more wrong or right than the other. They're both just different ways to interpret this problem. So both are biased. Both have their unique biases, again, based on where you put the brackets. And one thing that we're going to be talking about, and really the focus of fuzzy, is how we can turn those biased estimates, we can remember that they are indeed biased, remember how we're adding bias, and we can turn these types of biases into variance instead. So this is where I'm going to introduce Monte Carlo arithmetic. Actually, I guess before I do, does anyone have, while I take a sip of coffee, does anyone have any questions? Perfect.
I think you're good on questions, but I'll encourage people. We're at the end in like 8 minutes or so.
Perfect. Thank you. So basically, Monte Carlo arithmetic is where we take inexact floating point values and treat them as random variables. So I'm not going to spend too much time on this slide. I guess, lingered here while I was taking my drink. But the concept or the premise is really, instead of being wrong the same way for every operation, we want to be differently but equally wrong for each one. In other words, instead of being wrong in the same biased way, we can be wrong variably. So this is a different representation of Monte Carlo arithmetic that might be a little easier to grok. Again, we basically, this is as it's implemented through a tool called Verificarlo. Now, one thing you'll notice in the links that'll be on one of my last slides is Verificarlo and fuzzy are very, very tightly related. And again, I'll get to what those are very shortly. But the premise is basically you have some source code, whether it's written in C or Fortran, or even in Python, but you're using a recompiled Python interpreter. And when this is being compiled, turned into assembly code, you take floating point operations and you add a little bit of a workflow to them. And now we're going to kind of break through what this workflow turns into. So it starts with upsampling data. Then we're going to add some noise, do our instruction, add some noise, and round our results. So again, imagine we have the sum we're seeing up here, 6,000 plus 5.452. So again, we would see rounding absorption error in the case of this operation because we don't have enough bits or digits of precision to represent all this. So first thing we do is we upsample. We pad them both these values with a bunch of zeros. Then we're going to add some noise because basically what we're saying is beyond the precision of the data we have, we don't know what the precision is. So instead, we essentially are adding a random variable centered between 0.5 and negative 0.5, and we just sample data from there, and any possible sampling of these results is equally plausible. So we sample this, we add our noise, then we perform our operation on these upsampled data. So here we are, this is our results of the addition instruction. Then we add a bit more noise because, again, we aren't really sure what the result is. So we do it again in the same place with our upsampled bits, and we can round our results. So again, in this case, we're introducing perturbations at the level of machine precision, which means that we don't know what happens beyond the decimal point in the case of the 6,000 or behind the 2 here. So we're deciding to add perturbations there. You could conceivably add perturbations closer into the more significant, or to distort the significant digits of your data. However, that would depend on your context.
You have about 5 minutes left. Just want to warn you.
Okay, cool. Thank you. So when you're doing these perturbations, you can either perturb up front, and this is called precision bounding. Basically, this is saying we're assuming that there's a limited precision in the data we're providing, or you can do it as on the outputs, and this is called random rounding. So what this means is essentially we can take any arithmetic operations with this technique. And one thing that's important to remember is that, sine, exponent, log, all of these more complex and common operations are implemented at the very base level through arithmetic operations. We can take them, we can define the way we want to perturb them, we can make their error probabilistic, and when we put all this together inside of our scientific tools, we can evaluate how stable they are. So we've done this already with several libraries. So we have something, a tool on GitHub, or a set of environments on GitHub called Fuzzy, as I mentioned here. And we've perturbed, or we've instrumented GNU's libmath, BLAS and LAPACK, as well as the scientific Python stack. And this set can grow. All you need to do is recompile libraries. This set in particular was, chosen for no particular reason other than we have use cases that needed it. But it can extend for sure. So you can basically then take our fuzzy environments and add them quite simply to your code. So this is just an example recipe where, for anyone who's familiar with Docker, this is essentially doing similar to a multi-stage build, or actually this one might exactly be a multi-stage build, where you can basically create your image and then you copy over the perturbed or instrumented math libraries. This example exists on our README, so I won't linger too long here. Again, as long as you go to the repo, you'll see exactly this. But the premise is basically it doesn't take very much to copy over the perturbed libraries and start doing your analyses. So now we can do, or actually before I move on, there's a few different use cases we can talk about here, and I'll go through them quickly just so we don't run out of time. But basically, there's a few different things you may want to do. The first may be detecting loss of precision in your tool, or detecting places where your tool starts to fail. So this is a fun series. This is just a simple geometric series that asymptotically approaches the number 6. However, and if you were to solve it analytically at iteration 30, you'd get the number 6.0056. It's pretty close to the correct or convergent answer. However, regardless of the precision you're using, by iteration 30, solving this using floating point data, you will pretty stably diverge from the correct path and converge on the number 100. Now, this is an example of just that. So we have the orange line that is the true solution of this series as you get to iteration 30. And what we did was we wrote a little script in Python that just implemented this series and ran it 5 times with Fuzzy. Now what you can see is these massive error bars that pop up right when we lost precision. Basically, the tool is completely stable until this point when all of our data kind of becomes garbage. So basically what this allowed us to do is we know that this portion, the place where we're losing data, the place where we're losing significance in the pipeline, the function diverges, is happening right here. So pretty much imagine you have an iterative process. You could use something like Fuzzy to detect when that process becomes unreliable and either restart your process from the previous one as a checkpoint. You could potentially grab your results from right before it went awry, depending on your context. But the idea is it allows you to identify points of failure. Now, because I have probably negative time, I'll go quickly through the next examples, but basically you can evaluate the trustworthiness in results. So you can basically perturb results with this numerical uncertainty and compare that to other forms of variation. In this case, I was comparing the difference between individuals to the difference I got within an individual and just the numerical error that's associated with the results. And similarly, you can actually augment data sets by using these fuzzy results and aggregating across them. So you can really apply this anywhere inside your analytic pipelines. I see you're backmaticking, which means that I'm out of time. But anyways, you should head on over to Fuzzy and Monte Carlo and contribute, ask questions, get involved. And I'd like to just give a huge thank you to the whole team that supports all this.
Great. Let's everybody thank our speaker. And our speaker is extra support person. I'm glad you're here, Johan. Great. Nice round of applause. Thank you so much for the really interesting talk. I think you had a nice lively chat going. Some nice emojis. So I also loved the interactivity of your talk. I think that was a great idea. So let's see. I think looks like a question just got added to the Q&A. Oh, we have a few. Okay. Well, I'll show the first one.
Is that divergent series available? Yeah, so if by available, you mean like the code to generate it and the data and all of that? Yes, it's all available through an example in the Fuzzy repo. Mm-hmm. So if you head on over to, I'll post the link in the chat just to make sure everyone has it. But if you go there, it's you can find this example.
Okay, great. Okay, so the next one, can a similar thing be done with differentiable calculations like JAX?
I'm not exactly sure I know what JAX is, so sorry about that. But
Bradley, do you feel like coming on the stage? You could, and you could describe it if you feel like it.
But I mean, to kind of more vaguely answer, any form of calculation you're doing, any arithmetic operation can be perturbed in this way. Okay. So really, it doesn't depend on what you're doing so much as that you're doing arithmetic and with floating point data. One important thing that I didn't mention too is that we're never perturbing things that are exact, that can be exactly represented when we're doing analysis this way. It's only perturbing things that are at the limit of the machine precision.
Cool. Yeah, I think that's thank you. Yeah, this is a great talk. Yeah, I think my question was kind of like, can you whether autograd or other kinds of approaches to get a sense for the differential stability of at particular values of a function. But I think you kind of answered that. I think it's this is like a really cool injection of that LLVM. That's really cool.
Yeah. Thanks. Johan is more to blame for the coolness than me.
Okay, well, thank you for the question, Bradley. Okay, the next question can be from Luca. Can this be used to treat physical uncertainties and measurements as well?
Yeah, so that's a great question. So one thing I mentioned with the slide, or with one of the slides I kind of had to jump through, was that you can really use this to compare to other forms of uncertainty. So the first thing I'd recommend if you're trying to compare to, say, uncertainties and measurements is really begin with an experiment where you're looking at how the uncertainty introduced by floating point arithmetic and at what precision you need to do it and all these sorts of things, how that compares to the measurement uncertainty. And once you find a good counterpoint, once you find some way to simulate your machine error or measurement error, which we've done in various contexts, then you can absolutely use this as a stand-in. So one thing that I'm currently working on using this for example, is to look at mitigating batch effects. So the differences that you'd have when taking data from one center versus another, for example. So you could totally do that. Again, the first step is really just evaluating how the numerical error compares to your measurement error.
Okay, great. Thank you, Luca, for that question. Okay, our next question is from Andrew Reed. How does this relate to uncertainty quantification? It feels similar, but I'm not an expert in either.
It is uncertainty quantification. So there's different subfields here. Uncertainty quantification can take different forms. For instance, one popular form is you perturb just the inputs and you look at the way it gets your outputs of your function. Again, this is kind of more similar in spirit to a condition number, but these are all just different sides of the same coin. And again, they have different implications on your tools and your results, but they're all different sides of the same coin, and really it's kind of context dependent where it makes sense to use which kind.
Okay, yeah, that totally makes sense. And thank you, Andrew, for the very open question. I think it's good if we're all admitting what we do and don't know. So thank you, Andrew. Okay, so we're running a little bit out of time. I think this can be our last question from Luca Danini. What's the minimal way to run this tool? I.e., do we need Docker or can we just pip install something?
So unfortunately, there's no pip installing, simply because this isn't quite a Python library as a way to study the stability of your Python libraries potentially. But you can run it without Docker. So again, if you go into the GitHub repo, there's installation instructions for the tools that we're using. Really, this depends on something called Verificarlo, which is really doing the heavy lifting, and Fuzzy is just an application of this towards entire environments. So you could really, recompile them, follow all the instructions. It's all public, of course, and you could use it in whatever configuration makes you happy. Docker is just probably the easiest way, so you don't have to reinstall all of the dependencies as well.
Okay, yeah, that's helpful. Well, if you feel like installing just in an install party, you can make your life extra hard, right? So
exactly.
Well, thank you again for the great talk, Gregory. And let's thank our speaker one more time. In 5 minutes, the lightning talk start. I encourage all of you to head over there shortly. Otherwise, join the Gather Town a little bit later. Thank you again, everyone.
Thanks so much.